Hello everyone. Welcome to the fourth lecture of the lecture series on open channel flow. In this lecture, we are going to discuss and explain the energy depth relationships for open channel flow. So, in this chapter, we're going to explain a very important concept in context of open channel flow, which is the concept of specific energy. We have already discussed about the total energy of open channel flow, which can be given by the first equation on the slide. Capital H equal to Z plus Y cos theta plus alpha into capital V square by 2G. Here we have discussed before that Y is the normal depth at the section, Z is the elevation of the channel bottom, and V is the mean velocity at that section. Now imagine that we shift the datum. The datum has been shown on the figure, in the figure on your right. The datum is a horizontal one here. Now imagine that the datum, we shift the datum to the channel bottom, and that's how we arrive at the energy which is called or which is defined as the specific energy of open channel flow. So if we do that, the expression of the specific energy becomes capital E, that equals to Y plus alpha into V square by 2G, where alpha is the kinetic energy correction factor. Now, if we consider a channel with considerable or appreciable width and depth, where the velocity profile, the vertical velocity profile, can be assumed to be more or less uniform, and the channel is prismatic. So in that case, the specific energy can be written as E equals to Y plus V square by 2G, where alpha, the kinetic energy correction factor, is approximated as 1. So this expression of specific energy is the classical expression, and from now onwards, unless otherwise mentioned, we will consider the specific energy to be E equals to Y plus V square by 2G. So the specific energy can be defined as the following. I will read out the definition. Specific energy is the amount of energy per unit weight of the fluid, with the channel bed considered as the datum. The specific energy of water in a channel is the summation of the dynamic pressure head and the static pressure head. So the second sentence here is also very important. As you can see from the expression of the specific energy, that specific energy is the sum of the static pressure head given by Y, or the flow depth, and the dynamic pressure head given by V square by 2G. The concept of specific energy in open channel flow was actually introduced and defined by Russian-American engineer named Professor Boris Bakhmetev in the year of 1932. He introduced the concept of specific energy, and the specific energy from then on is used extensively in open channel flow, in the analysis of open channel flow. And this concept has been very important in explaining the critical flow conditions and classifying the flow as critical, subcritical, or supercritical flow, which we'll discuss very soon. So the way the specific energy is defined, it is evident that the specific energy remains constant for a uniform flow. note that the two terms of in the expression of the open channel flow, in case of a uniform flow, these two terms remains constant. So evidently the specific energy remains constant for a uniform flow, uh, whereas it can vary in a varied flow like gradually varied flow or in a rapidly varied flow. It can either increase or decrease. Also note that this is the point where specific energy differs from the total energy defined before. Total energy is something which always decreases in a real open channel flow, because there is always some channel resistance, some channel the resistance offered by the channel bottom and sides, which offers friction, and there is a frictional head loss in the flow. So total energy is always decreasing in the longitudinal direction. So the specific energy can be written in terms of the flow discharge as E equals to Y plus capital Q square by 2G capital A square, where A is the flow cross section. So in this case, the specific energy becomes a function of the flow depth and the discharge here. So if we write the flow cross section in terms of the flow depth in the second term of the expression of specific energy, then you can see that it becomes the expression of a cubic parabola for a constant discharge. The E versus Y variation, or the specific energy versus depth variation, is shown in the diagram. And remember that this is the shape of a cubic parabola, and this is known as a very famous specific energy diagram. You can see the diagram above, where an arbitrary channel cross section has been shown and the cubic parabola has been shown, and there is you can see that the specific energy is plotted on the abscissa, whereas the flow depth has been plotted on the ordinate. You can also notice there is a line OS which is at a slope of 45 degrees with the horizontal. So you can obviously guess that this line represents the line where specific energy equals to the flow depth, or E equals to Y. So in this cubic parabola, there are you can find that there are two positive roots. It's a cubic parabola, so there are three roots, but two of those roots are positive. So two of those roots are going to represent two depths, two flow depths in context of open channel flow. So of course, the figure on the right hand side in the specific energy diagram, the cubic parabola which is shown here is drawn for a specific constant discharge Q equals to Q1, and for this specific discharge you can see for a specific for a given specific energy E1, there are two depths possible, and with the two depths are given by here as PR and PR prime. So again, for a given specific energy E1, there are two depths possible. Those two depths are two positive roots of the equation of cubic parabola, and the ordinate pp prime represents the fixed specific energy E1, and the flow depths for those for that given specific energy are given as ordinates by ordinates PR and PR prime. These two flow depths are called or are known as alternate depths of flow. So evidently here the flow depth PR prime is much greater than uh, the flow depth given by PR. Now, as we mentioned before, that the line given by OS represents the line on which specific energy equals to the flow depth, or E equals to Y. It can be implied, or you can deduce that uh, the ordinates here given by P prime R prime and the ordinate given by P prime R, by noting these two ordinates, you can guess that these uh, two ordinates P prime R prime and P prime R gives the velocity heads for the corresponding alternate depths, and this is very important. So of course you can see that for the positive root on the upper limb of the curve, so uh, for the flow depth is large, so the flow depth for the positive root on the upper limb is given by PR prime, and the flow velocity is given by P prime R prime. So you can imagine that for the flow depth for the flow represented by the upper limb, the flow depth is large, whereas flow velocity is small. The value of flow velocity is small. Whereas just oppositely, the for the flow condition represented by the lower limb of the cubic parabola, you can see that the flow depth is small. The flow depth is given by capital P, capital R, whereas the velocity is represented by P prime R. So the velocity is high, whereas the flow depth is small. The, the flow condition, which is given by the upper limb, thus known as the subcritical flow, and the flow conditions, which is represented by the lower limb of the cubic parabola, is known as the supercritical flow. So always remember, subcritical flow is something is a condition in which the flow depth is large and the flow velocity is less, whereas a supercritical flow is a condition in which the flow depth is small, whereas flow velocity is very high. That's the difference between subcritical and supercritical flow. They are just opposite to each other given the characteristics of the flow. Note that here on the in the diagram on your right, that if we increase the specific energy in the on the abscissa, the difference between the alternate depths increases. So as we shift the line PP prime to the right, you can see that the difference between two alternate depths, they increase. Whereas if we move the ordinate PP prime to the left, the difference decreases. So if we keep on shifting the ordinate PP prime to the left, we will arrive at a condition at a point we'll arrive at a condition at which the line PP prime will become tangent to the cubic parabola curve. And for that condition, you can see two alternate depths are not possible. Only one uh, uh, flow depth is possible. And this particular condition at which there is, for a given discharge, only one flow depth is possible, and the the specific energy is minimum at that point. So this flow condition is known as the critical flow condition. The particular flow depth, remember there are no alternate depths, there is only one flow depth, and that flow depth is known as the critical flow depth. And the specific energy E, the specific energy E with the subscript C corresponds to the critical condition is known as the critical energy. So you can imagine that the specific energy given by the critical condition is the minimum energy in the that can be seen from the curve. And if we shift the ordinate PP prime further left, there there will be no possible flow depths. So in other words, if the if the specific energy of flow for a given discharge is less than the critical energy, then there is no flow possible. Okay, so there is no real positive roots possible for the cubic parabola equation, and in other words, there is no such flow practically possible. Uh, so the so here now, as we have discussed that the critical flow condition is given by the minima in the specific energy curve. So it is possible to derive a mathematical condition or a mathematical statement or expression for the critical flow from the critical energy expression. And that's what we are going to do in the next slide. So at critical depth, of course, the specific energy is minimum. So for a fixed discharge, of course, and in the expression of specific energy, E equals to y plus capital V square by 2g, or E equals to y plus capital Q square by 2g capital A square. Remember the expressions of specific energy from the previous discussion. So in that expression, if we consider that the discharge is constant and also the channel parameters of width or the side slope of the channel cross section is constant, then the specific energy becomes the function of the flow depth only, or y only. So in that case, if we differentiate the specific energy with respect to the flow depth, or y, then we can write dE by dy as shown by the first equation on this slide. dE by dy equals to 1 minus capital Q square by g into capital A cube whole multiplied by dA by dy, and we can equate that to 0 as at critical condition E is the minimum. We have discussed before that the expression dA by dy equals to the top width of the flow cross section, or capital T. So we can write the critical flow condition as uh, we can q square into qc square, capital QC square, into capital T subscript C by G into capital capital A subscripted C cube equals to 1. So this is the mathematical condition of the mathematical condition for the critical flow, which says that the which is derived considering that the specific energy is minimum for a given discharge. Here, of course, the subscript C represents the critical condition. Note here that this critical condition is governed. Looking at the terms of the equation, we can conclude that the critical flow condition is actually governed by the channel cross section geometry and the discharge given by Q and T and capital A. So critical flow condition is not governed by any other parameters like channel roughness or bottom slope of the channel, etc. So we have discussed on Froude number before. Let's recapitulate that in context of critical flow again. Froude number, as we know, is a non-dimensional number, just like the other famous numbers in context of fluid mechanics or open channel flow. So Froude number is a non-dimensional number, of course, and like other non-dimensional numbers, it's a ratio where the numerator of the ratio represents the inertia force, and the denominator of the ratio represents the some external field. So in context of open channel flow, as the external field is of course the gravity field, and the gravity field generates the body force. So the denominator is given by the representation of that body force. The Froude number mathematically is given by the expression shown in the by the first equation on this slide. So if R equals to capital V by root under G into L, where V is of course the mean velocity averaged over the cross section. L here is the characteristic length, and we have discussed about characteristics length before. The length over which some characteristic of flow changes completely. So in context of open channel flow, the characteristic length can be the hydraulic depth. The hydraulic depth D is given by the ratio of the flow cross section to the top width of the channel, or D equals to capital A by capital T. So the Froude number in context of open channel flow can be defined as if R is equal to capital V by root under G capital A by capital T. So if we invoke the expression or the condition, mathematical expression of critical flow from the last slide, here we can easily deduce that for the critical condition, the Froude number equals to 1. So you can very easily deduce that from the expression derived in the last slide. So here this is a very important characteristic of critical flow, that apart from the condition of minimum specific energy at a given discharge, the Froude number of flow at critical conditions equals to unity. So this is a very important characteristic. So, other than so you can imagine that if the flow conditions are different from the critical conditions, the fluid number will also be different. So let's, for example, let's see the for the subcritical flow. So the as we discussed before that the velocity of flow is less than the critical velocity, and the flow depth is greater than the critical depth. So for subcritical flow, we can see that we deduce that the fluid number is less than unity. Similarly, for supercritical flow, where the flow velocity is greater than the critical velocity and flow depth is less than the critical depth. So for supercritical flow, the fluid number is greater than unity. So these are important characteristics of critical, subcritical and supercritical flow with reference to fluid number. Um, let's so in the discussion, whatever we had, there was one condition applied, that we discussed the specific energy in context of a fixed flow discharge. So there was a single curve on the specific energy diagram, and that single curve was for a given or fixed discharge. Now the discharge can be as well a variable, and for variable discharge the different specific energy curves can be drawn. As you can see, the diagram on your right, that there are different cubic parabolas have been drawn for different flow discharges Q1, Q2, Q3 and Q4, where Q3 is greater than Q2 is greater than Q1. So let's again take a given or fixed specific energy uh, in the diagram given by E1, which is represented by the ordinate PP prime. And for this fixed or given specific energy, as you can see, that if you go on increasing the flow discharge for this given specific energy, the difference between the flow depths, or the difference between the alternate depths, they decrease. So and if we go on increasing the keep on increasing the flow discharge, we can at one point of time we can achieve a condition or achieve a flow discharge at which the again the ordinate PP prime becomes tangential to the cubic parabola curve. So from the discussion we had before, you can imagine the condition of becoming tangent represents the minimum energy in the specific energy curve for that given discharge. But uh, but for that given fixed specific energy, uh, you can guess that this is the maximum discharge that is practically possible. So if we increase the discharge further beyond QM, so it's not possible to have a real flow depth for that given specific energy E1. In other words, that flow is impossible. So again, for a given specific energy E1, QM is the maximum discharge possible to pass through an open channel. And so for this flow discharge QM, uh, you can imagine that uh, uh, there is only one possible flow depth, and that's actually again the critical condition of flow. Now, is that the critical condition? Not. Let's check with mathematics again. Now, here what we did, unlike the last derivation where we considered the Q or the flow discharge to be constant, and um, we differentiated the specific energy with respect to the flow depth. Here we are varying the flow discharge, and uh, we're considering the specific energy to be constant or fixed. So in that case, the flow discharge uh, can be written as Q equals to please note the second equation on the slide. Q equals to capital A root under 2G under bracket capital E minus Y. So we are going to differentiate the flow discharge given by that uh, with respect to Y now. So if the discharge is maximum, as we discussed, then we can write dq by dy equals to root under 2g under bracket capital E minus y whole multiplied by dA by dy minus g capital A by root under 2g under bracket capital E minus y equals to 0. So we are equating that to 0 because that's a condition of a maximum. Now again, as dA by dy equals to the top width or capital T, and q by capital A equals to root under 2g under bracket E minus y, and the last condition is derived from the expression given in on the last slide. So we using these expressions, we can again arrive at the condition that gives us the same expression as as we derived for the critical conditions, that is q square into capital T by g into capital A cube equals to 1. So this is the same mathematical condition as we have derived before, and this is the condition of the critical flow. Hence, the critical flow conditions can be explained from another point of view, and we can conclude that the critical flow condition corresponds to the condition of maximum flow discharge for a given specific energy. So that's it for the time being. So we will continue our discussion on the energy depth relationships for open channel flow in our next lecture as well, where we will discuss or try to derive critical flow depths for different channels of different shapes and cross sections, and we'll also discuss about transitions in open channel flow. Thank you very much.